Okay, let's see. You just sound me on.
Yeah.
That's okay. I thought it was the microphone.
It means it is going to get boiled soon, so.
That's good. So that's what we want. Isn't it better that we put this water away because this is sitting in? You're not going to use this. All right. So we came all the way to realize that there are actually two type of points according to what we have done. So if you have a free boundary locally in the ball of radius 1, the free boundary problem of the type I've explained to you, then at each free boundary point you have the possibility of blowing up and using the machinery and getting the information whether the energy is going to be alpha n or alpha n divided by 2. So we're going to say if it's alpha n divided by 2, that's the low energy, then this has to be a good point. And we also saw that this value is coming from x1 plus the plus part of it. So it means that it's a half space. So we're going to look at those points. We also realize by upper semi-continuity of the energy at the point depending on x0 that these points are going to be, if you get one point which is regular, then it means the surrounding points have to be regular. So far regularity means that the energy is low energy. So that regularity doesn't mean much for us. So from here, having this low energy value, we're going to get to free boundary being actually graph, C1 graph. That's a huge step. But you will see soon that the techniques are actually not that involved once you come up with clever ideas. And this is what people did. And could prove that actually if you're close to a half-space solutions, then you're going to get this directional monotonicity. So you get Lipschitz regularity. The first thing to notice is once you are close to U0, if your solution is close to U0, then this is not only L infinity but C1 alpha norm because the conversion is a C1 alpha norm. Then you can actually use this in a way that we tried to use for the example we had at the beginning. So let me go back to that example just to remind us so we can come back to this very soon. So let's go back to the example. Yes, here is the example. So let me repeat this. So if you have a free boundary which looks like this, okay, so you have a free boundary looks like this, and then here is the free boundary, and what we want to do is to look at the directional derivative. And we see that if the function is non-negative here and 0, so it means that in this direction the EU is non-negative. If this is E1, let's say, and I can take anything, and this is E, anything which is very close to E1. And you realize that if I take a ball like this, then I cannot take E too far away from E1. But if I take a ball like this, I can go even further. If I take even a smaller ball here, I can go even further away. I can never, of course, go too far, but so the angle is always the cosine of the angle. Is that cosine? Yeah, that's always the sine. That is always positive. So we have a less than pi over 2 degree. No, that's cosine. So it's less than pi. So cosine is always positive. So what you get is that this is approximately, in this specific example, this is approximately like this. And this function itself is, of course, just like the function, or original function up to Einstein c to square root of it. So this function, locally, this is a linear function, almost a linear function. Okay? So it behaves linearly. It goes to zero, it's Lipschitz. So this is a Lipschitz function, but u is C11 function. So this derivative is like r, when you're staying away from zero with our distance r. It's like r. But u is like r squared. So it takes square root of that. So they are comparable. So when you're writing this later on, you have to be careful with that. You just have to adjust it. Think reasonably and adjust it. So this is what we're going to do. We're going to prove that actually we're going to get this. I'm going to change it a little bit because I have, if this is r to power 2 and this is r, and if I want to scale, so I may even put an r here. I can put an r in front of this and still have the same values. That's what we're going to do actually very soon. So let me go to the, so I'm running and I'm going to 12:30. Okay. So I need to organize this time-wise. Okay. So let me give you a few pictures. So what we have is this. Let's say this is the direction. The direction I'm taking xn, here, or e, or whatever. And then I know that the free boundary is somewhere here. Free boundary. And we know that two things happens. So this is v1. Okay, and the function, this is gamma r. The free boundary of ur is positive. This is a scaled version, so I've scaled it. And we know that ur is going to go 0 here. ur is going to go 0 here, somewhere. And this is going to be positive here. The free boundary is in between. And why is that? Because ur converges to u0 quite fast, and not only in L infinity but in C1 alpha. It means that the distance between these two guys are very small. So if you take anything here, I'm not specifying it, but I can actually do that explicitly with these values. And I can actually leave it to you as an exercise, but those values are correct. You just have to use what I'm suggesting, non-degeneracy, in one set, and the other one you have to use maybe something else. C1 or something. If you stay here, I don't know what these things are yet. So let's say this is delta. Okay, and I'm claiming actually that delta can be exactly chosen like that. I think. So let me go back again. Remember, this epsilon is coming from here. If you're close, epsilon close, then we can actually, if ur is, so ur minus u0 C1 alpha norm, I'm calling it, is less than epsilon over b1. We know that they converge. So I pick up an epsilon. I'm saying that eventually, for r small enough, I'm getting this. They converge. Both ur itself and the derivative of ur will converge to C alpha norm and C1 alpha norm together. And that means that this function has to eventually be 0 here. Because if u0 is 0 here, and if ur is never 0 here, then what happens, say, this is a point when ur always stays positive, then you know by non-degeneracy, in the neighborhood of this, UR is going to be larger than, let's say this is a new radius, call it a radius rho. UR is larger than rho, supremum of UR is larger than rho to power 2 divided by 2n. So it will be uniform positive there, and some supremum will be positive. So this is not going to happen for us, because the limit will be U0. So it tells me that there is no place here that there can be a free boundary. Because once there is a free boundary, I know non-degeneracy. Because we don't know, the picture might be something like this. It can happen, I don't know. And you see that this actually converges to 0. Eventually, this will be nothing here. So convergence might be very good, still C1 alpha. Okay? But I know that if there is a free boundary point here, then I know at this point, supremum of U over a polar radius rho, center Z is larger than Z to power, or to rho to power 2 divided by 2n. This is non-degeneracy you have in one of the lemmas. So it means that actually supremum of U will not tend to 0 if I have such a situation. But I'm saying that it actually tends to U0, and U0 is completely 0 here. So I'm getting a contradiction. So this means basically that this picture does not happen. I don't have this. So eventually I'm going to get 0. And actually you get this, if you look at this square root, that comes because square root of 2 epsilon, that's actually coming from this non-degeneracy. Okay? So this is probably a bit harder exercise, but we can actually do that. And we can actually get exact those values. I get this one 0, and then the other one I get a little bit differently because of C11. Okay. And you don't need to be so exact. For regularity, you don't need to be exact. But you know that it's epsilon dependent and it goes to 0. So it flats out. Free boundary becomes smaller and smaller in terms of epsilon. But I even know how flat it becomes, which is actually a lot of information. Which really, I don't think we use it. I don't remember it now, but I don't think we're using that. We're using that it's getting small. So what I just said is that free boundary is in here. So that delta is like epsilon approximately. This is approximately square root of epsilon. This somehow gives us stability that if you're close to a good solution, so U0 doesn't really need to be a half-space solution. If U0 is a good free boundary point, anything around it, if you have another one, this can be very general. It doesn't. They have nothing. They don't need to have anything to do with each other. This can be one solution which is regular, then any other solution with slight perturbation, the free boundary doesn't go away too far. And that already is a stability for free boundary. Because if you have a regular free boundary point, if you perturb your data, your Laplacian, your boundary data, the free boundary doesn't change in terms of regularity locally. It still remains regular. It's a very good result in the sense of stability. Because in many applications, not specifically for regularity theory, but generally in applications you don't have exact data, you might perturb it from one time to next time. I think you have to move or something. Okay, I shouldn't touch anything because I usually switch off the whole thing. Or maybe I should.
No, maybe I should come.
Okay, let's see. What movie do you want to see? Anyway, continue.
Switch them. Strip
No, everything is still in place. there at least. What? AC is working. Alright, so what happens is that that you get actually this flatness of the free boundary. You realize that these things here I mentioned, these are possibilities that we don't know. Or the function could be, the free boundary could go like this. Oscillate, but it converges to what you were expecting. So here is a picture. So you get flatness. So all I'm going to use is actually that if they are close to each other, the derivatives of this function and the derivative of this function are close to each other. And if you remember my example with the sine function or cosine function, I use that one function is larger than the other one, and if I can replace UR somehow with U0, then I can get that thing. So the question is whether I can do that or not. So if I can replace UR with U0, then I can get that. So the question is how do we do that? I cannot do it right away. I have to play with it a little bit. So here's how we do it. So if we take a low energy point, remember we have 2 points, two possible energy points, low and high energy points. So I'm taking a low energy point. If I take a low energy point, I know that UR is like U0 plus minus epsilon. It goes away from U0 just with an epsilon distance. And not only UR, but also the derivatives of UR. So this means that even if you take the derivatives, it's going to be epsilon plus minus. And now, somehow you want to replace it, but let's see how was that mechanism is working. So if we do that, then we see that UR actually, if you take the derivative of this and minus UR, combine it in this way, it has to be minus epsilon 0 in V1. Agree? Because if UR is very close to U0, epsilon close, if the derivative is epsilon close, then what you're going to get is that this difference is going to be sort of epsilon close, epsilon away from 0. Well, minus epsilon away from 0. It cannot become too small. It cannot become too negative. For some epsilon 0, I can actually arrange this. I can actually even take it, because of what I had earlier in the values, I can take this 1/8 over F. This is computational, so I leave it to you. You can actually get, this comes from my computations. No, sorry. This is if I take epsilon 0 very small, like epsilon 0 is smaller than this, then I can arrange R to be very small so that this is correct. This is a very important point. If you go past this point, then the rest will be useless. So let me repeat. So we know that U is very close, UR is very, very close to U0, which is a half-space solution. Half-space solution looks like this. Do we have lights here? So half-space solution U0 is x1 plus after rotation, power 2 divided by 2. Now, what is U0? dE U0 minus U0. In the direction E is close to E1. So this is going to be like, I can put my constants I have here, C times R. Okay, and this is going to be C times R. And this is going to be this is going to be the derivative of u0 in direction is going to be x1 times x1 plus, and 2 goes with 2, then you get direction e1 times e. Yes? Something like this. This is what you get. Minus u0, which is x1 plus. This is the value I have. And when r is very close, so this is in D1, basically. And then you realize that if I choose first r very small, I get the closeness that u r to be replaced by u0 up to that epsilon. So if I go back here, I have c times r, dE u r minus u r. This plus some epsilon 0 is larger than this guy. If r is chosen very small, this is larger than this. And this itself is exactly like this. But now, if I choose C large enough and direction E very close to E1, this is going to go larger than or equal to 0. You can verify this. So try to verify this. If you choose C large, so first R is chosen, small. So if you choose R small, you get this. R is now fixed. So at this stage, R is fixed. Now I can choose C very large, so that this is going to be larger than 0. And then E is not going far away from E1. This is going to go larger than or equal to 0. And you realize now that this whole thing here is non-negative. So that means exactly that this guy is larger than minus epsilon 0. Okay? So that's the proof of that this is going to be larger than minus epsilon 0. But this is not what I want. I want to prove that's larger than or equal to 0. I don't get it. I get only it's larger than minus epsilon 0. So having come to this stage, then you need a device. So in the polar radius 1, you have this left-hand side, the combination of these functions is larger than some small value. And remember, I can choose epsilon 0 whatever I want to, but then I have to play with C and R. So let's fix epsilon 0 to be 1 over 8n. That is a constant which actually comes in computation later on. And then we get this. So how do we continue from here? Okay. So my claim is that I claim that once that is true in the polar radius 1, in a half ball, exactly in the half ball, this has to be non-negative. This is a quite strong claim. I'm claiming a function is larger than minus epsilon 0 is going to be larger than 0. It's larger than equal to 0 in a half ball. But of course that function is a very specific function. It satisfies a very good PD. And I'm going to show you how it works. You remember the proof of non-degeneracy? That's what we're going to use, that type of thinking we're going to use. So I can assume R is 1 just for simplifying everything. Doesn't really matter, you can work with a scale version. So R is 1, let's say. So we don't keep track of R's here. And a good exercise for you is, why can we assume R is 1? You can do scaling, and you can replace and rephrase things. So suppose you want to prove that that's not negative. So suppose there is a point where this function is actually negative, and then you will soon see that's a trouble thing. So here's the picture. You have this free boundary. You have lower radius 1. You have a point. You have a point in a half ball. Y. And this is negative. So let's call that function along with something else, W. So W, you remember we had something like this before with the non-degeneracy. We added this function who compensates the Laplacian of this guy. Laplacian of this is 1 or minus 1 in this case. And Laplacian of this is also 1. So I'm compensating that Laplacian. So Laplacian of this is already 0 because it's a harmonic function. Derivative of u is a harmonic function. And minus 1 plus 1. So the whole thing is a harmonic function. And in the Borel radius, 1/2 here. So y is here. This is the center. Something like this. Maybe I go with the free boundary. If this function is negative here, and it's harmonic inside where everything is, then the minimum of this function has to be less than or equal to 0. So the infimum of this function has to be less than or equal to 0. Because it already has a negative value. So infimum is less than or equal to 0. And the infimum has to happen on the boundary because it's a harmonic function. Okay, so W has a minimum which appears on the boundary. So what possibilities do we have? So there are two boundaries. One boundary is this guy. One is this one. What happens on this boundary? On this boundary, the derivative is 0. This is 0. The function is positive. So on this boundary, the function is positive. But the function has a negative minimum, and it has to be here. So W at some z here must be negative. Anyway, the infimum there is negative, so the infimum of the W on the boundary of Borel radius r, the center or 1/2, center is less than or equal to 0. Okay, so on the Borel radius 1/2, this guy is going to go what? R to power 1 to power 2, so R is 1. We are working with R is 1. So it's going to be 1/4. 1/4 times 2n, that's 1/8n. That's the value 8n is coming from. So you're going to get that infimum is negative. It means that so just let me go back so you see the picture again. This is negative. It means that if you go here, so this is less than minus 1/8n. So if this is negative, then you just take the whole thing here, that's 1/8n, and then you're going to get exactly this. The whole thing here is less than minus 1/8n. But recall that we said this guy is larger than minus epsilon 0, which is 1/8n, or less than 1/8n. So you get a contradiction. So that's a simple proof of Lipschitz regularity. You were expecting something much more fancy, but this is actually fancy because you get a very simple proof, and it took many years before the proof came. This simple proof came, So Louis Capelli gave this proof in 98 sometimes. So the first proof is in 77, very involved. Second, he gave another proof, which was easier in 81 sometimes, 82. And then in 98, this proof came. So it took sort of 20 years to simplify the proof. This is a beautiful proof, and actually works perfectly in many scenarios. Okay, so what we have, you take any free boundary, then you know that the cone, so here's the picture, you take any free boundary, you know that if it's regular, then you're going to get that the free boundary is actually, so let me open up the other page as well. So it means that if you have a free boundary which is regular in the sense of energy, low energy point, so there is a direction here, E1, and other direction function is increasing in this direction. This is E1 and this is E, and it's increasing in this direction. So it means that any point here has this cone. That's the cone property. So that means that the free boundary locally is a graph of the Lipschitz function. So I can represent it like x n is f of x prime. X prime is the rest of the variables. And there is a constant, well, not exceeding the cone. The cone is not exceeding the cone's value, the opening of the cone. And I think that actually I can open this cone more and more, because if I take smaller r, my function actually is coming much closer to u0. So I can really do that for any direction I want to, but I have to take very small walls. So that means that if I go much closer, this cone's open on both sides, and that's exactly the definition of being C1. So the definition of the graph is C1. It means that these cones can be opened if you take smaller walls, can be opened more and more. That's geometric definition. You should definitely do that. That's calculus 1, basically. You should definitely do that. It's good for understanding it. So here's the picture. You get all these cones on both sides. This is called cone of monotonicities. So in all these directions, for any E in the cone, for any vector E in that cone, your graph is monotone in that direction. So it's a graph. So if a function is graph in too many directions, if you take a cone, and you take all vectors in that cone, and now take that vectors and say you have a graph, and that graph is increasing, or your function is increasing in all these cone directions, then that's called cone of directions, monotonicity in cone of directions, and that's what you get. So what you have to do is you have to go back to the original scaling, and you go back to the original scaling and you get this, that the free boundary actually stays above this graph, and below is, it's exactly the graph, and above it is the set when u is positive, but this row is very small. You can improve that Lipschitz norm here, delta, by taking it much smaller. Basically, that's the explanation I gave you for geometrically, that you can improve this. There is another way of doing this by Harnack's boundary Harnack inequality. You can actually do that, but I will not go through that. You can do that very fast. But that, it doesn't give you C1 only, it gives you C1 alpha. This one gives you just C1. The other method gives you C1 alpha, which is much stronger. But then you have to use the boundary Harnack inequality, or boundary Harnack, it's called boundary Harnack, for Lipschitz domains. Then you get C1 alpha. Okay, so So this is the regularity theory that I plan to tell you about. So what we will do is we will do little exercises, and then I will take a few questions. Then I was planning to do a little bit of what are the recent. That was what you're thinking about? Or you're thinking about something else?
No, you had written numerics, but I don't think you plan to do numerics.
I don't. Is there anyone doing numerics? Or? No, we will skip numerics because I don't see how we should do that. I'm not a numerical person. I was hoping you could do numerics. Okay, this is how we do. Then we take early break. We come back. And the first alternative is that the first hour I will do the general, and then the next hour we will do exercises and homeworks. So we'll discuss that. Okay. So then after lunch I will do recent theory. We'll just discuss what are the new problems, two phases, systems. I will just give you the flavor of the problems. So these are not going to be included in your exam. It's just going to be a flavor of different problems. And then the last hour we can go through the exercises we have suggested. So we can prepare you for the exercises. And I guess that will be homework they will do also. And the exercises. And that will be their grade. I think that's the best way. Anybody disagrees?
No, you already decided that.
You already decided. Okay,
I suggested, they were like, okay, I said, we can do it this way because the problems are kind of.
And you cannot have exam just sitting and doing it. That's not going to work.
They need to just go through it.
It doesn't help you to learn.
Yeah.
And you cannot learn this in a very short period of time. So we will work through some of the exercises at the heuristic level, understanding level, and then give you a little bit of ideas, hints, and then you take home for a week or something, and then just then then you will get your certificate once you're done, yeah?
Yes.
That's the plan. Because you get credit for this course, you know?
It's one credit course.
Okay. That's very little for...
Yeah, for the content you did, right? Yeah.
That's
I
very little.
I agree. I mean, next time, this is my first time. So.
Okay. This is 5 credits, 7.5 credit actually. This is 7.5 credit at my university, but that was over the whole semester.
Yeah, and then this is
You do all the details and there's a lot of things. You will be happy to get that 7.5, yeah? Maybe you should bargain a little bit more.
I think maximum is like it is 1 or 2 credit course because one really cannot do much in 1 week. But I think now maybe
It's 2 weeks now because they don't work at home. Part of this is homework.
no.
So I'm writing on your behalf. So let's see.
We can try to make it 2, but
No, because this is reasonable that it's going to be 2 weeks.
yeah, because they will work hopefully next week as well.
If they don't, they will probably not manage. So they have to work.
Yeah.
So that's probably 2 credits is good.
Now,
Probably get money from them to save this. I think 2 credits, because we do it a whole semester. I used to do this course whole semester, a little bit more rounded, of course. And then,
visits kind of it.
yeah. Okay, let's take a break and come back fresh to the next part.
Maybe after lunch, right?
What is lunch?
At 12:30 is anyway lunch break, so I think.
So we take a break now.
Yeah.
That's what I'm thinking.
Yeah, then it's
I was not
fine.
going to continue.
No, it's okay. As soon as he says we will start, we will start. Doesn't matter. The lunch time will come at 12:30.
Yeah, because I want to start on something new. I don't want to
and
just.
have a break in between.
Yeah, that's not.
I think
It's better to
nice.
start fresh one. We go 1 hour or something. 1 hour, 1:30. The first one is 1 hour. Then you go 1 hour 30 for.
The first one is 1.5 hour, and then the last one is 1 hour.
Let me switch.
So it's up to you. you. Yeah.
We switch. We take 1 hour first.
Yeah, I think it's better.
Right.
And then, so then I will ask
Because I
the.
need more time to work. I want to have a few specific exercises that we discussed.
Yeah, and I will ask him to bring the tea earlier. So it's
That's
just.
a good idea. Are we going to get the light? Because we cannot work here if there's a light. You see, we did a lot of machinery to come to something which is very easy. But once you have done everything, this part is easy.
It's when you are showing that the regularity part. I did think of Harnack inequality, but of course I don't know how we are going to how does one
Yeah,
do
you
it?
can think of Harnack inequality maybe. There's a paper by Athanasopoulos and Pefarelli. He did very nicely actually. That part. But this is using nothing.
Yeah, this is like kind of just using comparison function and getting it nicely.
So that one was things like this. If you have already Lipschitz,
Yeah.
oh, you have to prove, sorry, Lipschitz you have to prove.
Yeah.
Yeah, you prove Lipschitz and then this gives you C1 anyway.
Yes. True.
But if you want to go C1 alpha, then if this is the graph, something like this, if I remember it correctly. So let's say the function is u, you take directional derivative x1 and tangential direction, something like this, and then e1, something like this. And then you prove that this is Harnack, boundary Harnack says that this is C alpha. If this is C alpha, then these guys are representing actually the graph.
Right.
So u is what? U is the graph. If this is the graph, then you have to power it to some function. And then you can put it here, and then you get actually that f is going to be, the derivative of f is going to be C alpha. That's the way they do it. But you have to use boundary. Right.